All right. Well, thank you for the great information or introduction. Can you hear me in the back? Is this loud? Is loud enough? Louder? How about this? This? Okay. So thanks for the introduction. I'm going to be talking about changes to HBNet that I've been playing with to design hydrogen bond networks. If you don't know what that is, we've seen some examples in the earlier presentations, but a hydrogen bond network is a connected component of hydrogen bonds. We've seen them a lot lately in the Rosetta community at interfaces. This is a protein-protein interface that's actually native. And I'm going to be talking about ways to design those. So why design hydrogen bond networks? The short answer is that they improve interaction specificity between macromolecules, proteins. But if you've seen Scott Boykin talk, or we had a few posters today or this week too, there are many very neat things you can do. They've been able to design very interesting de novo protein-protein interfaces, and the most recent progress that I've heard, at least, that they mentioned this week was now they're starting to use those to make logic gates, which I think is very cool. But the short answer, specificity. And then what makes these networks hard to design? The first is that hydrogen bonds themselves are very sensitive to structural conformation. You really don't need that much movement between the atoms in order to get a drastic change in energy. And because of this, any hydrogen bond network designing protocol it would be beneficial to be able to handle large amounts of sidechain sampling, particularly extra chi sampling, which I'll talk about a bit later. And the second point is that it's very unstable to design polar atoms that are not satisfied, that are not participating in hydrogen bonding. So when you introduce polar atoms into an interface, you want to make sure that you're really that it's satisfied as well as you can get it. Now, like I mentioned, Rosetta already has a protocol that designs hydrogen bond networks called HBNet by Scott Boykin and friends. Shown here is one of their proteins that they put together that's shown in their paper last year. That's cited at the bottom if you can read that. And you can either run it at interfaces, which is where it's that I've seen it used at least more often, or in protein cores. Most of my talk today is going to be focused on protein interfaces, but a lot of it can be extrapolated to the general case. My lab mates, when I joined the lab, had tried to experiment with it, and the experiences have been more hit or miss. HBNet either didn't find anything, or if it did find something, it took a very long time to do that, or it would just run and we'd have to kill it before it found anything. And maybe that's more suited, maybe that's more the case for our larger full interface design protocols, because clearly they got it working very well to design things like this. And because of this, you can't always do a whole lot of extra chi sampling, so you might not always be getting the best hydrogen bond that you could. So I'm going to briefly talk about how HBNet works a little bit under the hood, but more as an overview. So consider this protein-protein interface, green protein, blue protein, and I put a little disk on the residue positions that we're designing at. Now at each position, we're going to have a rotamer set. We're going to have a series of sidechain conformations that we are going to be considering for that position. So now if we visualize that we're making a graph structure with a node or a disk for every rotamer at each position, and then connecting them with lines or edges for the ones that form hydrogen bonds. So for example, this column has every rotamer, a node for every rotamer considered at this position. And sorry, my mouse is very small. Can you guys see that? And two of them can form hydrogen bonds to this node. The goal of HBNet, oh, thanks. I might still use the mouse if that's okay, so both people, both sides. Then the goal of HBNet is to find a connected component within this graph that does not have two disks at the same position, because that would be assigning two rotamers to the same residue position, which you don't want. You want every residue position to be fully satisfied, and you don't want clashing between any of the nodes. And so this is already a lot to keep track of, and it gets worse when you consider that the graphs that we're playing with are quite large, quite a bit larger than what I showed on the previous slide. This is actually the smallest I could find. This is a one-sided protein-protein interface design I've been playing with. And if I did anything larger, it'd still be rendering on the computer, and I wouldn't be able to show you. But HBNet actually runs very fast on what I'm showing right now. The way HBNet finds these connected components is it accumulates a library of paths where each path starts at a hydrogen bond that crosses the interface, and then it works outward until it either cycles back on itself or it hits a... is Scott here? What's the word? It hits a hydroxyl. I'm sorry. Right? It's hydroxyls and cycles. Those are the two. I'm simplifying. I'm simplifying a little. So, for example, if the path won't end with a glutamine or something that requires more than one hydrogen bond to satisfy it. And I believe, I don't know for certain, but I believe the reason for that is that they didn't want to sign up for residue, for networks that could not be satisfied, because if it ends, with a glutamine, then it's possible that there's only one hydrogen bond that could go into that, and maybe it wouldn't be fully satisfied. So then you end up with this big list of all these paths, and the next step is to merge them together. So these first two, for example, have a common edge, so they can be merged into this larger network. Then these two have two common edges, and this network is a little bit more complicated. It has it's not just a path, it has branch. And then this one is effectively actually the sum of all the top three. And this top list is actually quite long, so you get a large number of networks out of this. And this is the step that I'm going to be talking about a little bit more, because there's room to improve this. The number of total merges you can make is 2 to the number of paths that you have. And this is a very large number. Now, HBNet doesn't go to all 2 to the n of them, because not all of them are connected. They might be in different parts of the protein, and a lot of them have clashing. But still, this is a large number, and this is something that I think is part of the reason for the slow experience that me and my lab mates have had. This also makes extra chi sampling expensive, like I mentioned before, because as you add extra chi samples, you get very similar networks out of it. And it just extends that list of paths that you have so much that it really hurts this 2 to the n number. A second thing I'd like to talk about is the path library isn't fully complete. There are some paths that aren't being sampled. Like I mentioned in the previous slides, that it won't end with a glutamine. And part of that is for satisfaction reasons, but those are the underlying reasons for that is assuming that that's a buried position. It's possible that if that glutamine is solvent exposed, then you won't have a satisfaction issue. So there are some networks that have solvent exposure that HBNet won't be able to sample. And I've actually tweaked HBNet to have fragments that either end in cycles, end in hydroxyls, or additionally end with solvent exposure. And this actually improves the result, but because of this first bullet point, it makes it much longer to run. So today I'm going to be presenting a Monte Carlo protocol that addresses both of these issues. So now in this new protocol, you go through every hydrogen bond that crosses the interface, and you use that as a seed to branch off of randomly. So here, for example, there are four possible ways to grow. There's 3 over here and 1, but if you remember that large, there's more than 4 usually. And you just randomly add one piece at a time until you can't grow anymore. And you might do this hundreds or thousands of times for the same seed and get different networks. And it used to be that at the very end, at this point, we would check and make sure that it's satisfied, and if it is, we store it, evaluate it later. But what we actually found to be very beneficial is at every step, so now I'm going back in time, at every step, after we add any node, we check to see if it's fully satisfied and then store it. And we got a huge increase in quality because a lot of times there will be satisfied subsets, or subnetworks, I guess, like what I'm showing here. This isn't done growing, but it might be as large as you can get and still be satisfied. An addition of either of these 2 additional nodes might cause dissatisfaction. And by allowing the Monte Carlo HBNet to also check these networks, we actually got a great improvement in output quality. Then how do we randomly grow out? So we have this seed, say we're a few steps in, so the black is what we've already have, and we're choosing between green, blue, and red. We tried a few different probabilistic ways, like maybe uniformly, like there's a 1/3 chance of adding each one, or maybe weighing it by the strongest hydrogen bond is most favorable, or even we tried some temperature scheduling where at first it starts uniform and then you get you go for the stronger, and then the reverse of that where you end up more uniform. But the best that we've got is you look at the number of downstream compatible nodes that are favorable with the network. So for each of these, we look 1 level downstream, and we count all of the nodes that are compatible with what we have so far in black. And using those as a metric really benefited us. So in this example, so the probability is 1 plus the number of downstream nodes that are compatible. So the blue would be the most probable to add, regardless of how strong that hydrogen bond is. So now we've got 2 protocols, and it's time to test them. And I used a one-sided interface design test, mostly because that's what my project is a little bit more interested in. And that's also where we've seen HBNet be a little slow. So I found 591 protein-protein interfaces in the PDB, all of which have 2 chains. So there's no third or fourth to get in the way. And all of them are polar enough to have a hydrogen bond design there because all of them do have a native network design there. So the protocol has no excuse to not design something. So I ran HBNet and Monte Carlo HBNet, one side able to design, the other able to repack, and I measured the wall time, or the runtime, and the mean score of the 10 best networks. The score metric I used is the sum of every hydrogen bond energy plus a small penalty for buried unsatisfied polar hydrogen, and we didn't allow any buried polar unsatisfied heavy atoms. Now, I did this on 599 interfaces, but we're not going to go through all of them. I picked a few at random. But I looked at more to make sure that they're representative. So we got this one, 31 designable positions, 37. So that's the size of just one side of the interface. So it's roughly double that if you include both sides. We have runtime in log scale on the x-axis, score on the y, negatives better. And we have a few different points for each protocol. They correspond to different amounts of extra chi sampling. So the first point, no extra chi sampling, EX1, 1, 2, 1, 2, 3, 4. We don't actually have an orange point, an HBNet point for 1, 2, 3, 4 because that took longer than a week. So didn't include it. Likewise on the right, it actually, it only took EX1 to make HBNet take longer than a week, whereas Monte Carlo HBNet could do 1, 2, 3, and 4 in a few hours. And in both of these, I think Monte Carlo looks pretty favorable. It's for the same sampling level, it's faster and it gives a better result. And especially in the cases where HBNet doesn't run in the week, Monte Carlo looks quite good. So now if we look at all 591 as a whole, this is, now runtime is on the y-axis, and this is a function of the problem size, the number of designable positions. And again, runtime is log scale, so the Monte Carlo points they roughly fit a line. And they're faster than HBNet. 8 of the HBNet runs didn't finish within a week. For example, you can see some of the Monte Carlo points here don't have an HBNet that they correspond to. And these finished, 0.1 hours is 6 minutes, so maybe these took 7 minutes, whereas their HBNet counterparts took longer than a week. But not all of the ones that didn't finish were large. The smallest HBNet that didn't finish was at 45. So even this end of the spectrum was running into issues. And even the ones that did finish, there's roughly 4 orders of magnitude. They could take anywhere from 36 seconds, this line is, to, this is 100 hours. Where Monte Carlo HBNet, none of them took more than 7 minutes, I don't think. And then 28 of the HBNet runs, they finished, but they didn't find any networks, where every Monte Carlo found something. And the benefit of the Monte Carlo, too, is if you don't find anything, you just run it again. It's not deterministic. HBNet is. This last point I want to make is we've also played with non-interfaces. So this is a small helical bundle that we've been playing with. And I tried running HBNet and Monte Carlo HBNet to make a hydrogen bond network in this core. And HBNet didn't finish within 24 hours. But Monte Carlo gave us some pretty good results in a half hour. I missed a point in the previous slide. This is all with no EX flags. So if HBNet doesn't finish, you can't just decrease the amount of sidechain sampling. You'd have to decrease something else because this is as low as it gets. Though I'll admit that, these were some very large problem sizes that we were playing with. 300 positions is quite big. So in summary, the Monte Carlo protocol is able to, it can improve HBNet's ability to sample networks. We can sample more space now. And it's also more tunable. There's really only one parameter you have to tune. I guess there's 2. There's extra chi sampling, but the more fine-tuned parameter is just the number of trajectories you run. You just give it a number, I don't know, maybe it's a few million, and Monte Carlo HBNet divides it evenly over all the starting seeds, and that's really all the user has to worry about. You can double that, and it's roughly double the time. It's linear, and so now you can really tune it to be a week-long protocol if you're willing to give it a week, or if you want it to be just one step in your Rosetta script, you can make it only take a few minutes, and you'll still get something. So with that, I'd like to acknowledge Scott Boykin, who's been a huge help. This is actually all a product of his idea. It was his idea to have Monte Carlo a merging step. My PI, Brian Coleman, and Andrew Leverfey have been huge helps. And then an undergrad in our lab, Sarah Wu, has helped me out with Monte Carlo. So thank you. It's not a complete sample space. Just because the changes you made to the solving? Yeah. Now we can sample more networks. I don't know if I perfectly represented that, Scott. Was that fair what I said about the solvent-exposed networks?
Yeah, I think the way that you're doing it, you're finding more of the satisfied subsets, where the deterministic HBNet doesn't find all of those subsets, so you miss some of those. I think.
Was it fair what I said about terminating with the solvent exposed, that HBNet doesn't really do that?
It'll terminate if it's solvent exposed and can't find anything else,
but not all the time.
But not all.
So now Monte Carlo.
Will find something else that
So Monte Carlo is more, it has less bounds. It'll report anything that it finds. And it can search anywhere that has a hydrogen bond edge.
Is it possible then to do a fair comparison, like a comparison where HBNet will find everything?
I mentioned that briefly before, where I modified HBNet to well, there's already a store subsets option, but I made a middle ground there where it'll store terminating with solvent exposed positions. And maybe that would be a more fair comparison for the score axis, but that just takes so long to run because of the big O 2 to the n that I couldn't really do it on too many.
So one of the questions is, given a Monte Carlo search, how close to the best possible are you finding?
We're searching that right now. That's what we're studying. We find it only really for a given starting seed to branch off of, it really only takes 50 or 100 trajectories to find the best that it can make. Yeah.
So you mentioned that you start with nodes that have lots of downstream. Do you actually expressly calculate the centrality, or can you talk more about how you determine who those best guys to start with are?
Well, we actually start with any hydrogen bond that crosses the interface. The downstream part is more choosing what's the next node to add, the probability of that. And HBNet already calculates clashes. So we just have to go through all of the downstream nodes and check to see if they have a clash. I think it's...
It's not just connectivity, it's also which guys need.
They need to be compatible. Yeah, they need to not clash, and they will only be considered if they're connected.
So it's like between the centrality times crappiness of energy.
We don't take into account hydrogen bond strength, if that's what you mean, anymore. We tried. It didn't seem to be too... It was basically the same as uniform. It didn't matter too much.
But when you do that, you do have the full weighted network in memory.
I'm sorry?
Like you have the whole weighted network of potential hydrogen bond strengths in memory when you...
They exist. We just don't... It's not beneficial to use them. We haven't found.
One more question?
Yeah, that was cool. I was just wondering whether you might get a further speed up by using something like a graph reversal algorithm like Scott does, just to find the longest paths to begin with, and you start some Monte Carlo trajectories from the longest one, sort of take away these steps.
Yeah, we could. Or maybe I also thought about staying near the interface and not, like excluding paths that go too deep into the core, because we've had that too. But the trajectories don't take a whole lot of time. But you're right. That's a good, yeah. Thank you.
All right, let's thank the speakers again.